All right, we're in section 3.6 where we're going to prove theorems about perpendicular lines. So just like when we talked about lines being parallel, there were postulates and theorems that helped us prove those lines are parallel. All right. Same thing goes here. We have some theorems that allow us to um, show that lines are perpendicular. So by definition, for two lines to be perpendicular, they have to intersect at exactly a right angle or a 90-degree angle. So we have some theorems that are going to help us out with that. So if we look at this first one here, theorem 3.8, it states that if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So we talked about a linear pair in previous lessons. Anytime we had a linear pair, we knew that those two angles were supplementary. And since they are supplementary, we knew that they added up. Their sums were 180 degrees. So what this theorem is telling us is that, okay, we have two angles that form a linear pair and they just so happen to be equal to each other. Well, if they're a linear pair, they're going to add up to 180 degrees, and if they are the exact same measurement, those two angles must be 90 degrees. So since they're both 90 degrees, we can then say that line G is perpendicular to line H. Here we have theorem 3.9, which states that if two lines are perpendicular, then they intersect to form four right angles. So it kind of piggybacks off of theorem 3.8, saying that, okay, well, 1 and 2 are a linear pair, 1 and 2 are supplementary, they equal 90 degrees. Well, 2 and 4 also are a linear pair and they are congruent, so they must both be 90 degrees. 3 and 4 are a linear pair and they are also congruent. That makes it 90 degrees. We could also say that 2 and 3 are vertical angles and 1 and 4 are vertical angles. And they're all going to be the same measure, which is 90 degrees or right angles. So if we look here, we have this diagram shown to the right. It says, can you conclude about what can you conclude about lines A and B? Well, lines A and B intersect to form a linear pair. And in the diagram, we see that angle 1 is congruent to angle 2. So we know that lines intersect to form a linear pair from angles 1 and angles 2. So by theorem 3.8, which states that if two lines intersect to form a linear pair and the angles are congruent, we know that the two lines are perpendicular. So by that theorem, A is perpendicular to line B. Here we have theorem 3.10, and it says that if two sides of an adjacent acute angles are perpendicular, then the angles are complementary. So basically, the conditional statement is if BA is perpendicular to BC, then angles 1 and 2 are complementary. Makes sense. Complementary means that their sums of the two angles give me 90 degrees. And by definition, perpendicular means they're at a right angle. Right angle means that they're 90 degrees. So, using some of these theorems that not only that we use today, but maybe we've used in previous lessons. Hopefully this is going to help us prove something for the diagram to the right. So it says here that angle 1 is congruent to angle 2. What they want us to prove is angle 3 and angle 4 are complementary, which means their sum's 90. So we go here, angle 1 is congruent to angle 2. That is our given statement. Next, it says if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So that comes from Theorem 3.8. And since that is the reason for this, that means the statement is going to be that we'll say that PQ is going to be perpendicular to PS. So with that being said, if we know that now these are perpendicular, now we can say that angle 3 and angle 4 are complementary due to theorem 3.10, which states that if line is perpendicular, so we're saying now that PQ is perpendicular to PS, and we have angles 3 and 4 that are acute angles, we know that they are complementary. Another proof we have here looks really similar, but now they want us to prove that angle QPS and angle 1 are right angles. So first off, we have the same given reason, same given statement. Now they tell us that PS is perpendicular to PQ, and we can use the same reasoning from the first proof we had on this page, and that comes from Theorem 3.8. That means that if two lines intersect to form a linear pair of congruent angles, then the lines are in fact perpendicular. That's from that theorem. So, and then the third statement is the proof. So now they're saying, okay, now we know that this line is perpendicular to this line. We can go here. We can also say that this is here, and we can also say that this is here, and this is here. We can also say that um, all four of those angles are right angles. So that comes from Theorem 3.9, which states that if two lines are perpendicular, then they intersect to form four right angles. Since they have all four right angles come into effect with angles Q, PS, and also angles 1. So theorem 3.11 is dealing with a transversal. The transversal states that are the statement is if a transversal is perpendicular to one of the two parallel lines, then it is perpendicular to the other. So you can see here that H is perpendicular to K, and since they gave us this right angle here, they're telling you that the hypothesis is H is perpendicular to K and J is perpendicular to H. Then, because of this theorem, we can say that now J is perpendicular to K. Theorem 3.12 states that in a plane, it says if two lines are perpendicular to the same line, then they are parallel. It's sort of the converse of the previous theorem. So now they're saying, okay, if we have two perpendicular, if we have two perpendicular lines, um, and they intersect that one line, that means that the two lines that are perpendicular to that one line are also parallel. So here we have a diagram here with lines R, S, and lines X, Y, and Z. It says determine which lines, if any, must be parallel in the diagram. So we have some fill in the blanks here. So it states that if R and S are both perpendicular to blank, So if you look here, the only one in the diagram where both R and S are perpendicular to is line X. Because right now, that's the only one that has two right angle symbols that share R and S and share the same line. All right. Y just has the 90 degree with R, and Z only has the 90 degree with S. So that's the only one we can, you know, with validity say that that is perpendicular to X. But so by theorem 1.2, we can now say that R is parallel to S. Similarly, lines X and Y are both both perpendicular to R. So now we can say that X is parallel to Y. So I go here and go here. Also, lines blank and blank are both perpendicular to S. Both X and Z. So now we can say that X is parallel to Z. Finally, because Y and Z are both parallel to X, you know that Y is parallel to Z by the transitive property of parallel lines. So that's how we kind of fill in the blank for uh, the explanations for that diagram. Okay, so here we have a diagram here to the right. We have some right angles here. We have lines that intersect each other. So we want to know, is C parallel to D? We want to know if C is parallel to D. And they want us to explain. The answer is yes. It is parallel to each other. The reason is C and D are perpendicular because here C and D are perpendicular to what looks like line B. Oh, I'm sorry, they're both perpendicular to A, my bad. They're both perpendicular to A because I got the right angle here and the right angle here. So by theorem 1.2, which again states that if two lines are perpendicular to the same line, then they are parallel. So because of that theorem, we can say that C is parallel to D. Yeah, because it's from line A. So now I can say it right here, boom, boom, they're both parallel. Next, they want to know if, excuse me, is B perpendicular to D? So they want to know if B is perpendicular to D, which in this case, there's no right angle in this case, but they want us to explain. The answer to this is now yes. Okay, since we've proved C is parallel to D, which we explained above, we can now use theorem 1.1, which states that if a transversal is perpendicular to one of two parallel lines, which in this case it's perpendicular to line C, then it's perpendicular to the other. So by that statement, we can now say that B is perpendicular to D. All right, here it says we have a section of a broad gauge railroad track is drawn on the graph. The lengths of the legs, the lengths of the tracks are parallel. What is the width of the track? It says the units of it says the units on the graph are measured in inches. You need the length of the perpendicular segment from one side of each other. Okay, so the first thing they're trying to do here is they want you to make sure that um, the two lines are perpendicular. They want to know if every single one of these lines are going to be perpendicular. So first things first, they want you to find the slope of, looks like QR, which is right here. So finding the slope of QR, since it's coordinates, we can use the slope formula like we did in 3.4. So m in this case is going to equal 55 minus 34 over 91 minus 71. All right, it's the y2 minus y1 divided by x2 minus x1. So we take 55 and subtract it by 34, and I get 21 here. And I get 91 minus 71, I get 20. And that is my reduced form. So my slope of that line, that red line we have up there, is 21 over 20. So now for this line here to be perpendicular, it has to be the opposite reciprocal. So our answer has to be negative 20 over 21. It has to be. So now we have to check it to make sure that it is in fact true. So PQ is 2974. So P is 2974 and Q is 7131. So we got what, 34 minus 74 over 71 minus 29. So if I take 34 minus 74, I get negative 40. And then I get 71 minus 29, I get 42. I can reduce that, I get negative 20 over 21. All right, so that's what we have here. That means that these two slopes are perpendicular. So now we can say that the segment PQ is perpendicular to the rail. So PQ is what? We have to find the distance. So to find the distance, remember we got to use distance formula, square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. So using basically these coordinates, so PQ will equal the square root of, and then it's going to be, what, 71 minus 29 squared plus 34 minus 74 squared. Like we said, 71 minus 29 was 42. Square that. I get the square root of 1764 plus 34 minus 74, that's negative 40. Square that, 1600. Add 1600 and 1764. I get the square root of 3364. Square root that, I get 58 inches. If I converted it to feet, it would be what, 4 feet 10 inches. And that is being able to prove theorems about perpendicular lines. Hope this helps. Till next time.